Hey, it's Dr. J. I'm back with part 2 of the division. In particular, long division is what we've done so far, so we might as well start with that. And I do have a new pen, so hopefully this one will look getting really low on the ink in my last lecture. And so I'm just basically going to pick up where we left off without too much of an introduction. But I will write some very explicit instructions. Use long division. And give the result in the form q of x, that's our quotient, plus r of x, our remainder, over d of x. All right. So I've got an example here. Let's do 6x cubed plus 5x squared minus 2x plus 1 over 2x minus 1. All right. So just a little bit of terminology before I get into what we're doing. I already mentioned Q is quotient, R of x is remainder, and D of x is divisor. We already have D of x right here. So D of x shows up in the problem. That's our divisor. It's the denominator. And then we also have P of x, which is really just a generic term for polynomial. This is called the dividend. And there is no mandate, that it must be called P of x. It could be called F of x, or it could just be called function. We could use any of our other names, G of x, or we could even just have no name at all for it. But in general, when I'm talking about polynomials and I'm talking about the divisors of polynomials, that's what I'm referring to as the dividend, which I will, in this example, call P of x. So basically what we're doing is we're saying P of x over D of x is equal to, and we're going to write our answer in this form, our result, Q of x plus R of x over D of x. All right, so I just kind of want to set the stage for that. So unless otherwise specified, so unless I give some other instruction, this is how I'm going to express the results. Now, I've already used up all my space explaining that. So in order to do long division, give yourself a little bit of room to work. So we've got our dividend, 6x cubed plus 5x squared minus 2x plus 1. And then our divisor is 2x minus 1. I think I made this suggestion in the opening video for division, that you can read it off the screen and then just write it down like this immediately, and then you'll save yourself at least a little bit of work. If you want some notational help on what we're actually doing, you can just kind of write this off in Scratch. I'll probably be erasing this pretty soon. This kind of just gives us our goal, so we don't forget what we're doing. Okay, and I already have gone over the long division algorithm in the last video. I'll explain it to a little bit less detail this time. So we're guessing how many times 2x minus, or 2x goes into 6x cubed. All right. So that would be 3x squared. And again, don't get too hung up on how long it takes to guess that. Some people don't see it immediately, but so just put something down and then multiply it, and you'll find out very quickly if it's the wrong thing. Yeah. So 3x squared and then 2x gives you 6x cubed. It's quicker to guess wrong or guess incorrectly and then find out that it's wrong and then give you a chance to guess again than it is to sit there and think about what you're actually going to do. So just do it and see what happens. All right. And then for your next term, don't forget to distribute. 3x squared times -1 is negative 3x squared. Okay. I like to use a different color when I change the sign. I know you don't always have time to switch, so if you're already writing in your pen or pencil, you can just continue to go. But for the sake of keeping track of the changes, I like to use the red to indicate that I've changed. And then I can cancel the leader, combine the like terms, wash, rinse, repeat, and that's the algorithm. You just do the same steps over and over again. All right, guess again. So what times 2x would be 8x squared? That would be 4x. Now, in your quotient, you must have either a positive or a negative sign, so that's positive 4x. So you multiply, you get 8x squared and negative 4x. And now I'm going to change the sign, negative, positive. Cancel the leader. Combine the like terms. Notice it's the same steps over and over again. And then bring down the plus 1. This one's in my way, so I'm just going to get rid of this. Another round. You can tell when you're almost done. We'll get to your constant. You know you're one step away from being done. So what times 2x is 2x? Well, those are already the same, so that's 1. 1 times 2x is 2x. And then 1 times negative 1 is negative 1. Now here's where it gets dangerous with the canceling, which is one of the reasons why I opened with this problem on this, is because it looks like we're done. We could just start canceling things off. But you're not. You have to do the sign change, which is the whole reason why I like to use a different color here. And that kind of tells me I'm not done until I see that. All right, now I'm done, and notice those ones are no longer opposites like they were a second ago. So I'm glad I didn't just jump ahead and cancel them. 1 plus 1 is actually a remainder of 2. Okay. And so let's label everything. Our original inside here was P of x, or dividend. Our original outside here was d of x, or divisor. And then our result up here, 3x squared plus 4x plus 1, that's q of x. Now, in general, you'll just be labeling these mentally, and it's mainly so that when you read the directions, you know where everybody goes. So I'm just kind of putting those off as mental clouds. And so the result is P of x over R of x. Now, this is just the original problem. All right, so that's just telling me what I'm actually doing. The answer is obviously over here, so I'm going to fill this out. And so we have q of x, 3x squared plus 4x plus 1, plus r of x over d of x, and there we go. There's our answer, or there's our result. Make sure you don't actually type this part. This part is just sort of stating what it is your answer represents. So this result represents the division of P of x divided by R of x using long division. Okay. Let's do another one. Same basic idea. I don't want to write all the instructions over again. Just ditto the same thing I just said in the last one, and then I don't have to take up all this space here. I'm also going to do what I recommended you do, which is as I read the question, so I'm reading it right off the screen. So I have 8x cubed minus 2x squared minus 23x plus 15 So that's the numerator, or the dividend, divided by 4x minus 3. Now I can just get right to work without having to rewrite it a second time. All right, let's just go for it. So what times 4x is 8x cubed? Oh, that's 2x squared. 2x squared times 4x is 8x cubed. 2x squared times negative 3 is negative 6x squared. Subtract, change the signs, cancel the leader, add 4x squared, bring everybody down, and start again. Okay, so the next guess looks like 4 is 1. And x. 1x times 4x will be 4x squared. You do have to put the positive sign, but you don't have to put the 1. You could just say x, and that would be fine. So x times 4x is 4x squared. X times negative 3 is negative 3x. This is almost the same problem, just practicing the same steps. Here comes the negative sign, so change that to negative 4. Change that to positive 3. Kill the leader. Negative 23, positive 3. So notice it's after I've changed the sign. Your mind might get impatient and try to do that step before you've actually changed the sign. It happens to me, which is one of the reasons why I talk myself through it, so that I kind of, can listen to what step am I on. All right, my next guess. What times 4 is negative 20? That'll be negative 5. So negative 5 times 4 is negative 20x. Remember, initially you want them to match. They have to be the same sign, and then you change the sign in the next step. If you try to skip ahead, it'll always be off. Your negatives and your positives will be off by 1 cycle, so you got to be careful. Negative times a negative is a positive 15. Here comes the negative, changing that to a positive. This was a positive, which I just leave as blank, so I'm changing it to a negative. And the key difference in this example is now we have a remainder of 0. So the 0 remains, or the 0 is the remainder. The quotient remainder. Finally got a 0 remainder. I haven't really been emphasizing this in all the examples because I didn't want to be disappointed in every single one, but I was actually hoping that we would get a 0 remainder a lot sooner. But I just wanted to demonstrate that getting a 0 remainder is a special thing. And if it would have happened, in the first example, in the second, the third example, it wouldn't have seemed very special. So we did a ton of examples in which the remainder came out to be either a number or another polynomial or what have you, another expression. But when you get 0, well, not only are we going to be, present our answer the way that we're supposed to, because I still have to answer the question, by the way. So I have to do that, but I also want to emphasize what this means now that we have a 0 remainder. So we're going to stop and talk about this for a minute. So first of all, let's go ahead and answer the question. The answer is Q of x plus R of x over D of x. But because the remainder is 0, we omit the remainder part, and I hope it's for obvious reasons. 0 divided by 4x minus 3 is just 0. Right? So we're going to omit it because it's 0, and so our answer is only going to be 2x squared plus x minus 5, which is basically Q of x. All right, that's our quotient. So whenever the remainder is 0, you give only the quotient. You don't bother typing plus remainder or whatever. Which, again, if you think back to what I started this entire discussion about in the first part, it was all about basic math, right? And so if you say, what's 24 divided by 6, or somebody asks you what's 24 divided by 6, you just say 4. You don't say 4 plus remainder 0 divided by 6. I mean, you don't do any of that, although that stuff is still true. You just typically don't do that. You say, if a number is divisible by another number, then we just say what it is, and we don't bother. It's as if the remainders never existed, if everything came out perfect. Well, the odds of that happening turn out to be very low. So let's discuss our results before I move on. Again, what does this result mean? What it meant was that we had a polynomial divided by a divisor is equal to the quotient plus the remainder divided by the divisor. That's what this answer actually meant, right? But because the remainder was 0, that meant that our original polynomial divided by 4x minus 3, which I'm just going to keep it as d of x because it's easier. D of x is 4x minus 3, is only equal to the quotient plus nothing, because we omit this. I need this space back. So when the remainder is 0, your answer is just the quotient, 2x squared plus x minus 5. Right. Plus 0. We're omitting the 0. All right, now I can erase this. I don't need it anymore. So basically now I have p of x is equal to d of x, because I can just multiply both sides by d of x. And that gets the denominator out in front. And that would be denominator times the quotient, 2x squared plus x minus 5. But what was d of x? D of x was 4x minus 3. With no remainder. So I'm just going to erase these d's of x's here because they're gone. It's like they've canceled. And so now I just have my original polynomial. And so what did we just do? This means that we factored. Unintentionally. I mean, the problem didn't say to factor. It wasn't giving me the instruction to factor. The problem was telling me to divide. But we ended up with a 0 remainder. And so that means that our original polynomial, remember what p of x was, by the way? I've just been writing p, but it's actually 8x cubed minus 2x squared. Remember, it's the original dividend that I wrote down. Minus 23x plus 15 is equal to 4x minus 3 times 2x squared plus x minus 5. And that is no small feat. That is actually quite a task. I know that you've had some algebra before, beginning, intermediate, advanced, college, whatever your experience in algebra was. And I don't know if you remember, but factoring was sort of easy as long as the problems were easy. Like there was like a group of kind of prefabricated problems in which the factoring was pretty easy. But if you just threw out some randomly made up problem, then the chances of being able to do this were very, very slim. Okay, so this is almost a miracle, right? I mean, it's not. It's mathematical certainty, but I mean, it doesn't seem like it's going to happen very often. That you can take this polynomial, third degree polynomial. I don't know about you, but I don't think I could have done it. And then just gone from this to that without having this occur, without that zero remainder having happened. And so when something that special happens, we call this a theorem. This is worth noting. And so this is called the factor theorem. If the remainder is 0, when a polynomial, p of x, is divided by d of x. All right, so again, I'll label everything. This is p. All of this is p. This is d. Yeah, and this is q. Then d of x is a factor of p of x. You might make a note, q of x is also a factor. Yeah, we call it the other. Right? I mean, factors always come in pairs, right? So if you have an A, well, then you have a B, right? They come in pairs. That's how factors work, right? And so, but primarily the one that we're interested in is d of x. But you might make a side note, well, yeah, q of x is also the other factor. So basically it gives you the ability to factor a polynomial by using this theorem called the factor theorem. Okay. So I can't promise that this will happen again soon, but I will definitely mention every time this does happen, 1 out of 5 chance or something, maybe less than that, that we do, in fact, achieve a factor. Hopefully by the end of this section 5.4, by the time we get to the final, we'll have some way of really honing in on the factors and making this happen more often than just simply random chance. Okay. So let's do another example, and then I'll show you another way to write the final answer now that we have this idea. So let's do one. I don't know what's going to happen. I have not pre-screened these. I try to be as surprised, when it happens, or at least act surprised when it happens. So let's try something like, I don't know, how about 12x cubed plus 6x squared minus 9x plus 1 divided by 3x squared minus 2. And I got to erase this theorem, but we'll come back to it, and I'll certainly mention it. If it happens, if the remainder is not 0, then I'll have to say something else. Okay, so in this one, I'm going to show 2 forms of the answer. Let's start off of the result, putting it into the long division. 12x cubed plus 6x squared. Look for any missing terms. No, everybody's there. Divisor, 3x squared minus 2. And let's just go to work. So 3x squared goes into 12x cubed 4x times. 4x times 3x squared is 12x cubed. 4x times negative 2 is negative 8x. Comes the subtraction, so negative 12 and then positive 8. Kill the leader and repeat. So now we have, you see the mistake? Look at the mistake. 6x squared, 8x. This 8x actually belongs over here. It was negative 8x, so it's positive 8x. That's how important the columns are. All right? Had I just kept on going and driving, I would have driven right off the cliff. So now when I combine these, I'm essentially adding 6x squared to nothing. So that's 6x squared. And then that's negative 1x, or just negative x, and then bring down the 1. And then now 3x squared goes into 6x squared 2 times. But I got to make sure in your quotient, if it's positive, you put plus 2. So 2 times 3 is 6x squared. 2 times 3x squared. And then 2 times negative 2 is negative 4, and it has to be over in this column. Then here comes your minus sign, negative 6x squared, positive 4, kill the leader, bring down the negative x plus 5. Okay. So this is going to be our q of x, and this is our r of x. So the most common representation of a division problem, I wish these had names, but it's just form 1 is p of x over d of x equals q of x plus r of x over d of x. P of x over d of x is just the original problem. So that's 12x cubed plus 6x squared. That's your p. And then our q is 4x plus 2 plus r, which is negative x plus 5 over the divisor 3x squared minus 2. And again, the p of x was just the original problem. What was that? 12x. Yeah, 12x cubed. What was that? Let me look it up real quick. I have it here. 12x cubed plus 6x squared. I should do this more often. Minus 9x plus 1 over 3x squared minus 2. So that's the original problem here. And then that's equal to 4x plus 2. That's your quotient. Plus negative x plus 5 over 3x squared minus 2. Now, there is a way of combining the plus and the minus here to sort of make it look a little neater. I'm not going to do that in this example. If you do it, you end up having to pull this minus sign down and change some of the other signs. And I'm just going to leave it like this. One thing you can do is you can put parentheses around these. And that helps me develop my second form. The second form of the answer is where you multiply everything by d. To get rid of the divisor. That cancels the divisor in these two positions. But then you end up with the divisor times the quotient plus the remainder. Okay, and I just mentioned the factor theorem. So if the remainder is 0, this is what we would call factored form, if the remainder was 0. But if the remainder is not 0, it's just called the other form, or I'm calling it form 2. If I were to give a name to it, I kind of wish it did have a name. I would call it semi-factored, or sort of, or almost factored. Come up with some sort of loose term like that. So you have 12x cubed, my pen is going to die on me, plus 6x squared minus 9x plus 1. So that's p. Maybe I'll write it a little bit farther over here. So 12x cubed plus 6x squared minus 9x plus 1 equals d, so d is 3x squared minus 2, times q, q is 4x plus 2. When you use this form, you definitely need the parentheses. In form 1 up here, the parentheses were just kind of for show. I didn't really necessarily need them. And then plus r of x, which is negative x plus 5. And so that's the form 2, or the almost factored form. Our goal, as I finish this part of the video, and I'll also talk about this in my subsequent part, is to get a zero remainder. That's the goal. That's kind of what we're going for here. Okay, so now you've seen the two different forms of the answer. In my examples moving forward, I'll specify which form I want you to use. So my dividend is going to be 12x cubed plus 35x squared plus 34x plus 13. And my divisor is going to be 3x squared plus 5x plus 2. Okay, let's just go for it. Let's see what happens. So 3 goes into 12 4 times. It'll be 4x. 4x times 3x squared is 12x cubed. I better be careful here because this is a trinomial, so I've got more terms. 4x times 5x is 20x. 4x times 2 is 8x. Sorry, that's 20x squared. See how handy the columns come? It also is making me suspicious. Maybe we don't need the x's, you know. I'm starting to think, well, maybe there's a way where I can just write the numbers, and as long as I keep track of where they are, that there might be a better way to do this. So let's keep that in mind too. Change the signs. So those are all positive. If you don't put a sign, it's positive. So now I'm changing them negative. Killing the leader. Can't add these up. 15x squared plus 20, what's that? 26x. And then plus 13. And repeat. So 3 goes into 15 5 times. I better put a plus sign. It's positive 5. 5 times 3 is 15. X squared. 5 times 5 is 25x. 5 times 2 is 10. Here comes the negative. You can really get into a flow here, and it'll basically do it, solve itself, or evaluate itself, divide itself, whatever you want to call it. And you just sort of watch. You just kind of kick back, and this is like the first, machine. We're done, so this is going to be my remainder. That'll be 1x. 26 minus 25, and then plus 3. So again, this is r of x, and this is q of x. And so we're going to write our answer. P of x, so that's the original inside, 12x cubed plus 35x squared. 34x plus 13. Now, sometimes I've already done that for you, and then I just want you to fill in the blanks. So d of x is then here. This is d of x. So that's 3x squared plus 5x plus 2. Then q of x, 4x plus 5. And then plus r of x, which is x plus 3. You technically don't need the parentheses on the remainder, but, I already wrote them, so there you go. I know it's kind of tight here, but it is what it is. It's done. Hopefully you can see that. I can make it a little easier to read before I erase it. All right. And again, the remainder is not 0, so I don't get to invoke the factor theorem. But I can think about what just happened here, and maybe there's a better way. Maybe there's a better way. Let's do one more example. How about 2x cubed minus 4x squared plus 2 divided by x minus 1. Okay, here we go. The reason why I wrote this one down first when I could have just put it right in here, it's not, I actually did it intentionally because I want to discuss the missing term concept that we haven't had happen recently. There's a third power. It only applies to the dividend. There's a third power. There's a second power, but there's no first power. It's called linear x. So we're going to do a placeholder, 2x cubed minus 4x squared plus 0x. So there's our placeholder, and then plus 2. And then the divisor is x minus 1. Okay, so I just want to remind that pops up once in a while, and it usually happens when you are comfortable doing it the other way, and then all of a sudden you need a placeholder. You go, oh, God, I forgot the placeholder. So just to keep that in mind. Okay, so then x goes into 2x cubed, 2x squared times. So that'll be 2x cubed minus 2x squared. Change the signs. Kill the leader, bring down the rest, bring down your placeholder, you're going to need it, bring down the plus 2. All right. Now here's where the placeholder becomes important. When I go to my next guess, x goes into negative 2x squared negative 2 times, but this is an x column. So had I not had the placeholder, I would have thought I was done, because think about it, if this placeholder is not here, then that means this 2 would be right here, and I would have just thought that I was done. So the placeholder reminds you of what column you're in, and then if that's not enough to remind you, when you multiply negative 2x times x, you get negative 2x squared. So you sort of have a redundancy factor here in case one system doesn't catch it, you catch it in the next net. You have a multiple filter there. And then you got negative 2x times negative 1 is positive 2x. Change the signs. So that becomes positive, that becomes negative. Cancel the leader. And you see how important that placeholder is. 0x and negative 2x, that becomes negative 2x. Bring down the 2. Now you know you got one more round. So you got negative 2, again, times x is negative 2x again. That's coincidence. There's lots of 2's here. Negative 2 times negative 1 is positive 2. Change the signs. Everybody cancels. Remainder 0. Okay. So your remainder is 0. That means, by the factor theorem, x minus 1 is a factor of 2x cubed minus 4x squared plus 2. By the way, the other factor is 2x squared minus 2x minus 2. And so that means when we write our final answer, because the remainder is 0, we don't write it. So we just simply write 2x cubed minus 4x squared plus 2. That's our P, is equal to D. D was x minus 1. That's D. And then Q is 2x squared minus 2x minus 2. And then we will factor more in section 5.5. I'm sure you're all looking forward to that. Since this particular section is just about division, and then I've got a couple theorems, in particular the factor theorem. There's another theorem coming soon. But once we've gotten past all this division, then we will go back to this type of problem and factor it some more. You might already know how to do that. If you've done some algebra before, that might be something you're already capable of doing. If not, we'll just wait and we'll do it in 5.5. In fact, it's probably better to wait. If you start doing it now, it might spoil it. So. Okay, and then now we're finally going to learn a new type of division. If you've been paying attention through all of these examples, you probably noticed that the columns, as long as you were very, very neat with your columns, it really didn't matter what variable you were using, right? X, Y, Z, T. I'm sure most people were using X. But you might have noticed that the variable is not important. It's just a placeholder. Since the powers of x are simply placeholders, or indicators of place value, if we are careful, we can remove them. So for example, and I'm just going to say example, I'm not really going to number this one right now, because I'm not actually going to do the whole problem. So if you have something like, I don't know, 2x cubed minus 5x squared plus 4x minus 3, you can remove only the coefficients, including the signs, and we start off with an upside down division sign, so it's almost as if we've done the first step already. And we just make a row of coefficients. Okay. And so this gives us what's called the synthetic division algorithm. Now you got to leave a little bit of space here. Leave some space here. We call that row space. So you want to leave a nice row space. Keep in mind that this represented x cubed. And that's the only one you have to memorize, is the first one, or just keep it in your mind, that that first column actually represented x cubed. Okay? By the way, if you memorize that the first column is x cubed, then you don't need to memorize the rest. The next one is obviously x squared, and then the next one is just x, and the last one is constant. Okay? And then for the divisor, So this is for p of x. So you do this with the dividend. For the divisor, suppose the divisor was x minus 5. Let's use a different number, x minus 6. I want to use a number that doesn't appear here. Right. We take the opposite of the constant term. So that becomes your new divisor, and you put it right out here. So let me summarize that. For the dividend, remove the coefficients, keep them the same. So negative stays negative, positive stays positive, and so on and so forth. Just remove the coefficients, and then keep in mind what power they were, so that you kind of know this is cubed, that's squared, that's linear x, and then that's constant. Then for the divisor, now the divisor will always be x minus a number or x plus a number. It's a simple divisor, we call that. Simple linear, monic linear, if you really want a fancy name for it. Binomial. It's a monic linear binomial. Yeah. In other words, it's x plus something or maybe x minus something. It turns out that that's all we're going to be able to do. So just take the opposite of that value. All right? And then now this is your synthetic division algorithm. It's a little bit of a different rhythm than the long division algorithm. So here's how it goes. It's a lot faster. I'm just going to copy it up here. 5, 4, negative 3. And then 6 goes out here. All right? And so here's the algorithm, and I'm going to do it all step by step. First step, bring down the leading coefficient. Okay, so that comes right down here. Now I want to make something clear. When you bring that down, don't do anything to it. Just bring it down to get the ball rolling. Sometimes we refer to that as winding it up or setting it, kind of like you do with a clock or something. You know, you're getting the momentum going. You're winding it up, or setting the clock. Now you take the divisor, you multiply by the leader, and then you put the result here. Okay, equals. So put the result here. 6 times 2 is 12. Then you add. And if you really want to sort of just make a symbolic representation, you're technically adding in the first step also. You're adding 2 plus nothing and getting 2. So this adding concept is actually happening every time I draw an arrow going down, a red arrow going down. So negative 5 and 12 is 7. Then I multiply again. So it is an algorithm. You're going to repeat this process over and over again. And then put the result here. So 6 times 7 is 42. And then you add. So 4 and 42 is 46. Then you multiply again. 6 times 46, oh man, 276. I just guessed. Let's see if I'm right. 6 times 46, 276. Yeah. I would rather use the calculator and be right than try to be brave and try to be brave, go out on a limb and guess and be wrong, but I've done it both ways, believe it. I've fallen down. All right, the last box is always the remainder, which is nice about this process. You always know when it's going to end. All right, it's always just the very last number. We box it, and we call that the remainder. You do have to add to get it, though. That'll be your last addition. So negative 3 and 276 is 273. Okay. Now, to put the x's back, all right. R of x will always be constant. Which is a little bit strange notation. We still call it R of x because x was the original variable in the problem, but the remainder never has an actual x. But we're still just going to call it R of x. All right. Then Q of x, you lower the power by 1. Or reduce the powers by 1. So again, do you remember what that was a few minutes ago? I told you guys to keep in mind what the leader actually meant. So I put a little cloud around it and erased it a while ago. That was originally an x cubed, right? That's the only one you have to memorize is the first one. So now when you put the x's back, lower the power by 1. So that used to be x cubed. Now when it comes back, it's now x squared. All right. How about the 7? Well, if this was x cubed, then this was originally x squared. Yeah. That was the x squared column. So follow it down. Its power gets reduced by 1. So now it's just x. And then the last column, the 46, that's just going to be constant. So there's your Q of x. Now, that was my totally overly explained, overly dramatized with lots of different arrows and things to follow. I'm certainly not going to be able to do it like this every single time. So we just need a good summary of how it works, right? The divisor is the opposite. So d of x is x minus 6. Right? It's the opposite of that term with a variable of x, typically. I mean, although we could really get into some fancy math where you have other variables, but there's no need to make it more confusing than it already is. So we're just going to stick with x. Okay. And then the quotient, the quotient's down here. The dividend is exactly what it was, just with the x's removed. So that's 2x cubed, negative 5x squared. This is 4x. And then this negative 3 was the constant. So you want to have that sort of thing memorized before you try to do any more examples. All right, so let's do one now. I don't want to count this as an actual example. I mean, if you want to count it, you can. I think of more of this as a teaching tool, and then now you've seen the steps. Now I can jump right into it. Example. Okay, so now that we've seen all the nitty-gritty behind the curtain, mechanics of synthetic division, example 6 is revisiting example 5, the same question, but this time I'm going to do it with synthetic division, and by comparison, you'll see how much faster this is. So we take the numerator, which is the dividend. We strip out the coefficients, looking for any missing terms. Looks like there's a missing x term. The linear term is missing. And then for our divisor, we take the opposite of the constant term, so that's 1. And you're going to love this. Watch how much faster this is. Bring down the 2, or add nothing to it if you like to think about it that way. 1 times 2 is 2. Negative 4 and 2 is negative 2. 1 times negative 2 is negative 2. 0 plus negative 2 is negative 2. 1 times negative 2 is negative 2. Remainder 0 as we expected. Didn't we get remainder 0 last time? Yeah, I think we did. So we have q of x, or quotient. We lower the power of the original dividend. So now this 2 used to be 2x cubed. Now it's 2x squared. And then negative 2x. And then this is the constant term. The remainder is 0. Okay. And we can also state by the factor theorem x minus 1 is a factor of 2x cubed minus 4x squared plus 2. Yeah. Oh, consequently, the other factor is 2x squared minus 2x minus 2. Okay. So when you write an answer for something like this, it would be very simple. You would have your p of x, that's your dividend, divided by d of x is just equal to q of x. Typically, when the remainder is 0, we don't even state it. We just, I mean, unless the question specifically says what is the remainder, then you could say 0. But otherwise, you would just type the quotient. Or you can write it this way, again, depending on the instructions. You could put d of x first. That's your x minus 1, sort of like multiplying both sides by x minus 1. And then put q of x also in parentheses. And this is what we mean by being factored. So you've taken your polynomial and you have factored it into a first degree linear and then a quadratic. And like I said earlier, in 5.5, we'll continue factoring as much as we possibly can. Okay. All right, well, let's wrap up this lesson with a few more synthetic divisions. I never know if the remainder is going to be 0. I mean, I knew in this one because we'd done it before, but in general, it's kind of like to keep it as a surprise. I'd like to start working on some theory or some theorems that will help us to predict if that's going to happen. That would be very useful. I mean, it's nice to be surprised, but isn't it also nice to know what's coming, you know? I know human beings, we often feel anxiety if we're not sure what's going to happen. But so we can build theory or theorems in mathematics. We call them theorems that can help us guide our thought process so that we're not just shooting, you know, in the dark. Okay, example 7. Looks like my board's getting crooked on me. So our dividend is 1. Yeah, 1x cubed. There are no missing terms, so we got 1, negative 11, 31, and negative 20. Our divisor is 4, the opposite of negative 4. And here we go. Bring down the 1, multiply, add. Multiply, add. Multiply, add. Don't you love it? It's like, why did we ever have to learn long division? Well, the reason is long division works on every division problem. Synthetic division only works with these very nice divisors, you know, x minus 4, maybe x plus 4, or x minus 2, or something very simple like that. So now we have our q of x. Quotient is 1x squared minus 7x plus 3. And our remainder is negative 8. Okay, and then once you have your quotient, of course you don't have to put the 1. Once you have your quotient, your remainder, you can then enter in the answer in whatever form it's requested. Sometimes I'll ask for just quotient remainder. Sometimes I'll say write it in the form, q of x plus r of x over d of x. And then other times I'll say write it in the other, what I call the form 2, or the sort of factored form. Okay, I'll just leave that to you. Enter the answer as instructed. I got time for one more. I mentioned what happens if this divisor is positive. So let's do one like that. I think I'm off to Staples after this video to get a new pen because this pen is really dying on me. So I got x cubed minus 3x plus 2. Let's divide by x plus 4 this time. Nothing particularly special about 4, at least, I mean, there is if you're really into the philosophy of math, but it just seems like 4 is showing up quite a bit in this lesson. Is this 5.4? I think it is. All right, so our dividend, 1. Looks like there's a missing x squared term. Then negative 3, and then 2. And now our divisor is negative 4. Okay. Bring down the leader. Multiply, add. Multiply, add. Multiply. Negative 4 times 13 is negative 52. Add. The remainder is negative 50. So your quotient is 1x squared minus 4x plus 13. And your remainder is negative 50. Okay, since this is my last example, I'll go ahead and dress up the final answer. There are several forms. There's the p of x, that's p, over d is equal to q, putting down here, plus r over d. Okay, and I mentioned this earlier, if you have a plus and a minus. Last time I just left it, but you are allowed to, if you choose, this is of course an optional step, you can combine the plus and the minus into just a minus. When we do that, we normally put the minus out in front, and that's a little bit cleaner version of the answer, although I'll accept either one. Okay. This is typically how I want you to write the answer, unless you're instructed otherwise. That's what I want you to do. Okay, so in my final segment, part 3, coming soon, I will just focus on synthetic division, and I'll bring you another theorem. So until we meet again, this is Dr. Jordan. I'll see you on the internet.